Hi to everybody, I'm Linda Podio from INAF, Osservatorio Astrofisico Arcetri. In this talk, I will summarize the main result obtained in the context of ALMA-DOT, the ALMA chemical survey of Disk-Outflow sources in Taurus. So why ALMA-DOT? The final goal of ALMA-DOT is to characterize the chemical composition of protoplanetary disk. The question that we would like to answer is what chemistry planets inherit from their natal environment. This question is very timely now that JWST and Radial will study exoplanets' atmosphere. So what we would like to do is to link the chemical composition inferred from the study of exoplanets' atmosphere with the disk chemical composition inferred through ALMA observation. But what kind of disk we would like to target? So with ALMA-DOT, we decide to focus on young disk around class 1 protostars. And this is motivated by the fact that one of the breakthrough of ALMA is that ALMA images has shown that planet formation starts earlier than previously thought. Look at these beautiful images of disk around class 1 protostars. They all show rings and gaps, which are believed to be the signature of ongoing planet formation. Moreover, a recent paper by Tchionic et al. Compared the mass of solids in disk with the mass of exoplanets and concluded that while class 0 and 1 disk are massive enough to form the planet core of planets of mass similar to what observed for exoplanets, class 2 disk may not be massive enough to form planets. Finally, in a recent paper by Zhang et al., they show that the CO abundance sharply decreased from the protostellar to the protoplanetary disk stage. So this is why we decided to target young disk. However, from an observational point of view, young disks are still embedded in their residual envelope, so are more difficult to observe than disks around class 2 sources. Here you see before the arrival of ALMA, the iron 30-meter spectra of the embedded disk of DG-Tau in Taurus. You see, we detect emission from several molecules, but the spectra show a single peak profile, which is not consistent with disk emission. For this reason, Giotto et al. Concluded that the emission is dominated by the residual envelope and the outflow. And here, when the ALMA images arrived, we see that while 12CO is dominated by the residual envelope, CS and formaldehyde beautifully trace the outer disk region of the disk of DG-Tau. So motivated by this very nice early result, we started the ALMA-DOT observational campaigns. The main motivation is to obtain images of young gaseous disk with multiple molecules other than CO, that is dominated by the outflow and the envelope, to detect and characterize the distribution and abundance of molecules in disk, not only simple molecules, but also sulfur-bearing molecules and simple organics such as formaldehyde and methanol. And finally, we also want to image outflows and extended filamentary structures such as accretion streams onto these young disks. So to address this question, we asked and obtained 35 hours of ALMA time in different cycles and bands. We target 6 young disks around class 1 sources in Taurus in these molecules listed here. And thanks to ALMA-DOT, we already published a number of papers on the molecular structure of this disk, and 3 papers are still in preparation. So now we'll try to go through the main results. Let's start with this nice overview image by the ALMA-DOT 5 paper by Garuffi et al. This is the overview paper presenting all the sources in all the molecular tracers. You see on the left the 1.3 millimeter continuum emission, which probe the dust grain settled in the disk midplane. Then you see 12CO, that is always dominated by the residual envelope and the outflow emission. However, when we look at CS and formaldehyde, you see that in all disks, these lines beautifully trace the gaseous disk of the class 1 sources. In particular, we see that in all sources we detect a ring structure, so the emission originates from an outer ring, while the inner disk region is not detected. We see that CS and formaldehyde have always similar spatial distribution, and this is because the selected line have similar excitation conditions, but also because CS and formaldehyde are believed to be chemically linked, because according to chemophysical modeling, these species can be both efficiently formed in gas phase in the molecular layer through reaction of simple radicals like CH3 with either sulfur or oxygen. Then we see the CN emission, which is really poor and strongly anticorrelated with the continuum emission. And finally, the thioformaldehyde H2CS, which is published in a paper by Codell et al., which also presented talk on this topic. So go to look at this talk. And here I try to go more into the detail for a few sources. So here you see the molecules and this dust distribution in the disk of dg-tau B. In the two left panel, the 1.3 continuum emission before and after unsharp masking. So unsharp masking is a technique where we subtract from the original image a blurred version of it to enhance the contrast of substructures. And you see, in fact, in the second panel, we see dust substructure in the dust distribution already in this young source, so a signature of ongoing planet formation. And then when we look at CS and H2CO, you see again this ring structure, while we completely miss, as we see very well in the radial profile, the emission from the inner disk, because the inner 50 AU, the dust is likely optically thick. And we can also have absorption from circumstellar material. So because of this reason, to characterize the inner region of this young disk, we would need a VLA observation at centimeter wavelengths. Here you see the molecules and dust distribution in the disk of dg-tau. Again, in this source, we applied unsharp masking to highlight substructure, and you see in orange on the left and in red on the right, a ring of enhanced dust emission that is highlighted by unsharp masking. It is very interesting to note that this ring of enhanced dust emission coincides with the location where the continuum polarization due to dust self-scattering change direction. So you see the white vectors in the left panel change direction from parallel to the disk minor axis to azimuthal. And as polarization is very sensitive to the dust properties, so the dust grain size and opacity, for example. This tells us that at the location of this ring, we have a change of the dust properties. And interestingly, the molecular emission of CS and H2CO pop up just outside this ring. So this points to the fact that the outer disk chemistry is tightly linked to the dust properties and distribution in this disk. And here another nice case, the edge-on disk of IRA 04302, the so-called butterfly star. Since the disk is seen edge-on, we obtain beautiful images of the disk vertical chemical structure. So you see in the top left panel the 1.3 continuum emission, so the millimeter dust grain which are settled in the disk midplane, and then CS and formaldehyde have this X-shaped structure. This means that the bulk of the molecular emission originates from an intermediate disk layer that is the so-called molecular layer, where gas phase chemistry is efficient and we have photodistortion of molecules. As we move toward the disk midplane, you see that the molecular emission disappears because molecules freeze out onto the dust grains. So we have the freeze-out layer. This is the first direct probe with images of these two layers that are predicted in all the disk chemical modeling. Moreover, in this disk, we also obtained the first detection of methanol in a class 1 disk. You see on the left the moment zero map of methanol in red and overplot the formaldehyde contours. When we extract the spectra over the disk emitting region, you see that the methanol spectra peak show the two peaks in velocity at the same velocity as formaldehyde. So this confirms a disk origin for methanol. And then we compare the methanol to formaldehyde abundance ratio measured in our ALMA-DOT class 1 sources with the only value found in the class 2 source of TW Hydra and with the values found in comets, and also with values estimated in hot Corinos around class 0 protostars to reconstruct the chemical evolution. And what we see is that in protoplanetary disk, the values are 1 to order of magnitudes lower than in hot Corinos, so we have kind of a chemical evolution. As I told you in the beginning, CO is not a good probe of disk in these young embedded sources. Still, CO give us a beautiful images, is a beautiful probe of the V-shaped outflow cavities. For example, here you see the outflow cavities of DigiTau B and H2CO. Finally, as I told you, we also have emission from SO2 in a few sources, and you see here in H2CO, in blue is formaldehyde, in red is SO2, which only trace a tiny region of the disk. And this is the region where the accretion stream probed by CS impact onto the disk. So SO2 is tracing the accretion shock that is also commonly seen in class 0 sources. And with this, I thank you for your attention and I leave you with the results of the ALMA-DOT survey. Thank you very much.